Hello students, once again welcome you all back to another session on econometric methods course. Today we are going to see various approaches followed in the estimation of regression coefficients. In the last classes we saw how the regression model is constructed and how the regression model will look like. Today we are going to see various approaches followed in the estimation of the regression coefficients that we saw in the regression model. We are going to see today three approaches, very prominent approaches followed in the estimation of the regression model. The first approach is the linear ordinary least squares method. This method was first proposed by Carl Friedrich Gauss, a German mathematician, in 1795. Gauss first used this method to predict the future location of the then newly discovered asteroid called Ceres. In this method, alpha and beta, the regression coefficients, are estimated in such a way that sum squared difference between the observed and the predicted y of the model, that is the sum of the squares of the measured error. Euler's principle tries to minimize the sum of the error squares with respect to the coefficients alpha hat and beta hat. Let us see how the coefficients are estimated using this principle. Now let us explain the method of ordinary least squares. In this I am going to describe one sample regression function, and based on this sample regression function I am going to define the error term. Then I am going to minimize this error term to get the estimators of alpha hat, alpha and beta. Now let us see. So this is the sample regression function, and I derive the error term from this sample regression function. Ei is equal to yi minus alpha hat minus beta hat xi. This is no simple arithmetical manipulation. We are just taking this term to the left and we are swapping the terms. Then you get Ei is equal to yi minus alpha hat minus beta hat xi. Then the squaring of it, you get Ei square is equal to the square of the right hand side term. Then again you are summing this error for the entire sample, you get the error square, sum of error square as sigma I varies from 1 to n yi minus alpha hat minus beta hat xi square. The ordinary least squares principle warrants that we are going to find alpha hat beta hat such a way that the error is minimum. So this problem is very simple optimization problem, minimizing sigma I varies from 1 to n ei square with respect to alpha hat and beta hat. To get the minimum with respect to alpha hat and beta hat, we are differentiating the term sigma ei square first with respect to alpha hat and then with respect to beta hat. Okay, now differentiate 1. This is the first equation, we are taking this as 1 with respect to alpha hat. Then we get dou sigma ei square by dou alpha hat is equal to simple differentiation again minus 2 yi minus alpha hat minus beta hat xi whole power 2 minus 1 into, again you are differentiating this, so you get minus 1. So we are just reducing this equation further. So we are taking this negative 2 outside, then you get this second equation. Again we are differentiating sigma ei square with respect to alpha hat and beta hat. Just look at this terms. We are now differentiating with respect to beta hat. Here we get 1 extra minus xi, because if you differentiate this term you get minus xi. So this leads to, if you take minus 2 outside, then you get this term. Now, we are going to apply the first order conditions, namely the first two marginal values as 0. So, dou ei square by dou alpha hat is equal to 0 and dou ei square and dou beta hat is equal to 0. Then you get these two equations. We are just combining these two equations, and this leads to, if you take this term, only this term is 0, and so we equate this term to 0, and then we take this sigma inside the first equation, you get sigma yi. We are just taking this sigma inside, we are adding this term n times, so you get sigma yi minus n alpha hat minus beta hat sigma xi equal to 0. The second equation, right, similar to what we did now, we are going to take the sigma inside, we get sigma xi yi minus alpha hat sigma xi minus beta hat sigma xi square is equal to 0. These two we can rewrite this equation. Actually, we can take alpha hat beta hat terms one side and the other terms the other side, we get what is called the normal equations. So, we are just simple manipulation again. We take alpha hat beta hat one side. So, this is one side and the other terms the other side. So, you get this two equations. We call these two equations normal equations, and we can solve these two normal equations with respect to beta hat first. If you solve this simple simultaneous equations with two unknowns alpha hat beta hat, you get beta hat is equal to sigma xi minus 1 by n sigma xi yi divided by sigma I square minus 1 by n sigma xi whole square. Actually, this can be further reduced. You can multiply both sides by denominator and numerator by 1 by n, then you get the terms like this. So, you can write 1 by n sigma xi yi as, if you multiply 1 by n, you can take separately sigma xi by n and sigma yi by n, and similarly here in the denominator, if you multiply by 1 by n, we get the terms like this. So, you may write this term with 1 by n as this one. So, this can be, this is statistically nothing but 1 by n sigma xi minus x bar into yi minus y bar divided by 1 by n sigma xi minus xi x bar whole square. So, this terms again can be written like this. Now, this can be further reduced to sigma small xi small yi by sigma small xi square, where small xi is equal to xi minus x bar, capital Xi minus x bar, and small yi is equal to capital yi minus y bar. From the first normal equation, actually here is the first normal equation, we get n alpha hat. So, this equation, you take these two, this term the other side, you get sigma n alpha hat is equal to sigma yi minus beta hat xi. Finally, beta hat is equal to nothing but sigma small xi yi by sigma xi square. Of course, this is a shortcut. If you write in detail, this is sigma I varies from 1 to n small xi yi divided by sigma I varies from 1 to n small xi whole square. Here small xi is equal to capital Xi minus x bar and small yi is equal to capital yi minus y bar. Actually, this is nothing but deviations from means, from their respective means. So, small xi is the deviation measure from its mean and small yi is the deviation of capital yi from its mean. So, this is the estimator of beta hat. You can find the estimator of alpha hat from the first normal equation. So, this is the first normal equation. We will keep alpha hat one side and the other terms to the other side. So, if you shift that, you get this n alpha hat is equal to sigma yi minus beta hat sigma xi. Then dividing both sides by n, we get alpha hat is equal to sigma yi by n minus beta hat sigma xi by n. So, this is nothing but y bar and this is nothing but x bar. So, we get alpha hat is equal to y bar minus beta hat x bar. So, this is the estimator of alpha hat. So, from this principle we could derive the estimator of beta and the estimator of alpha. Now, let us explain method of maximum likelihood. In this case, we denote estimator of maximum likelihood method as alpha tilde beta tilde. This is found using maximizing the joint likelihood of x's and y's. Consider a regression equation. Y I is equal to alpha plus beta xi plus ui. Here yi and ui are stochastic variables. Both have PDFs and are normal. In this case, we are taking the PDFs as normal for illustration purpose. yi follows normal with the mean alpha plus beta xi and variance sigma u square. Each yi is independent because the sample is random samples and identical. In this case, the PDF may be written as f of yi is equal to 1 by square root of 2 pi sigma u square exponential of 1 by 2 sigma u square yi minus alpha plus beta xi whole square. So, this is mean and this is sigma variance given for every I varies from 1 to n. For the given PDF, we may write a joint likelihood of sample observations as L is equal to f of y1, y2 etc. yn. This is equal to f of y1 into f of y2 into f of y3 etc. to f of yn, because all the observations are independent. So, now we may write the joint likelihood function as pi that varies from pi of I varies from 1 to n f of yi. This is no multiplication symbol. Pi I varies from 1 to n, we may substitute the likelihood function of each observations, that is written as 1 by square root of pi 2 pi sigma u square exponential minus 1 by 2 sigma u square yi minus alpha minus beta xi whole square. Now, we may do some small manipulation, because this is exponential rule may be applied here, and the multiplication of this n times can be taken outside. We may get 1 by square root of 2 pi sigma u square whole power n exponential 1 by 2 sigma u square sigma yi minus alpha minus beta xi whole square. If alpha tilde and beta tilde are estimators of alpha and beta, then we may write the likelihood function as 1 by 2 pi sigma u square exponential minus 1 by 2 sigma u square sigma I varies from 1 to n yi minus alpha tilde minus beta tilde xi whole square. Interestingly, maximizing L is equivalent to minimizing sigma I varies from 1 to n yi minus alpha tilde minus beta tilde xi whole square, because in the previous case we are maximizing L, that is equivalent to maximizing exponential function of minus this term. So, they are monotonically increasing function, and so maximizing L is equivalent to saying maximizing minus of this term and otherwise minimizing the positive of the negative term. So, here we are converting the maximization problem into the minimization problem. So, maximizing L is equivalent to minimizing sigma I varies from 1 to n yi minus alpha tilde minus beta tilde xi whole square with respect to alpha tilde and beta tilde. This is equivalent to, very much equivalent to the method of ordinary least squares, and so we would derive the estimators as beta tilde equal to sigma varies from sigma I varies from 1 to n small xi small yi divided by sigma I varies from 1 to n small xi whole square, and alpha tilde is equal to y bar minus beta tilde x bar, which is very similar to the ordinary least squares, but the result will not be the same if you assume the likelihood function otherwise, because the individual PDFs, if the individual PDFs are other than normal distribution, we will not have this results repeated. And so, we may conclude that if the PDFs are normal, then the ordinary least squares method and the method of maximum likelihood method will yield the same results. Now, let us explain the third approach, namely method of moments. The main principle in this approach is we are matching the population moments with the sample moments. For instance, if you take the first moment, the average of x, the mean of x, mu x is matched with the sample moment x bar. The population parameter mu y is made equivalent to y bar. Otherwise, in the second moment, variance of x, the population variance or parameter, is taken equivalent to the sample variance small x square, and population variance of y sigma y square is equal to, is taken as equivalent to the sample moment s y square, that is sample variance. Similarly, the population covariance sigma x y is taken to be equivalent to the sample covariance small x y. This holds true for all kinds of moments. Let us take assumptions about u. This holds true for other moments. In this case, we are taking two assumptions about u. The expected value of u given x is equal to 0, and the covariance of u and x is 0. The corresponding moments in sample is, instead of expectation of u, the sample moment is 1 by n sigma I varies from n E I, that is average of error is 0. The covariance again we can write for sample here 1 by n sigma x I E I equal to 0. We may write this is equal to sigma I varies from 1 to n x I E I is equal to 0. Taking the description from sample regression equations, sigma E I is equal to sigma y I minus alpha hat minus beta hat x I equal to 0. So, this implies, as we saw before, n alpha hat plus beta hat sigma x I is equal to sigma y I. Similarly, the covariance moment sigma x I E I is equal to, we are substituting E I, that is y I minus alpha hat minus beta hat x I, we get the expression as sigma x I y I minus alpha hat sigma x I minus beta hat x I square, that is equal to 0. Now, we may write this expression as we are just now rewriting the equation in terms of alpha hat and beta hat. We may write alpha hat sigma x I plus beta hat sigma x I square equal to sigma x I y I. Now, we will take two equations, the first one and the second one. Writing this here, we have to solve this for alpha hat and beta hat. Now, we may say they are just like the normal equations we saw in the method of ordinary least squares. Just if you solve these normal equations for alpha hat and beta hat, we get beta hat equal to sigma x I y I divided by sigma x I square, where x I is the deviation from the mean and y I is the observations deviation, the value of observations deviated from mean of y. Now, alpha hat is nothing but y bar minus beta hat x bar. This is derived from the first normal equation. In this case also, the method of moments gives the very similar results as that of ordinary least squares method. So, again I want to stress that the alpha hat is taken as the estimate of alpha and beta hat is taken as the estimate of beta in this case. Let us summarize what we have studied so far. In this session, we have shown how the estimators are derived using different principles. Though they yielded the same estimators in all the three principles, they are based on different assumptions. We will see the implications of them in the coming classes. So, thank you.